Video number 4 adds a piece that I forgot called the Pauli Principle. And actually, one of the things that I didn't stress is, or I didn't understand, is that when we talked about atomic orbitals, we weren't even discussing the electrons. As I introduce the Pauli Principle, we'll start adding electrons to the atomic orbitals and see what kind of effects that has. And will lead up to concepts that are going to introduce the Slater determinants. I made a little correction here. This is called the reference kinetic energy. That's the ground state of hydrogen, and this orbital is occupied by one electron or no electrons if we just have a single proton out there in space. So think of the beginning of the universe. All we had were protons, a bunch of protons and loose electrons. And those electrons were attracted to the protons, and then the protons, hydrogen atoms, started to attract each other and create hydrogen molecules. And then all the other complexities of all the other complex molecules that occur in nature. Now down here, just to stress the same point that I made in the last video 3, that we have lower kinetic energy if these two centers come together and we have an electron that is attracted to both of these protons. And it takes a higher kinetic energy to achieve this factor where we have this node and it pushes these two apart, or it's seeking, and it takes energy to push the two apart. Here was the bonding orbital associated with this, and here's the anti-bonding orbital associated with this picture. Now, if an electron is attracted to the molecule, it has to make a decision. Am I going to go this way or that way? Well, I think you can understand from the way nature works, it's going to tend toward the lower kinetic energy. Now, that's with one electron, where we have an H2 positive ion. H2 positive ion only has one electron. What if another electron comes along? Well, it could occupy the higher kinetic energy orbital, or it could somehow join the first electron in this orbital. And that's the question. Can two electrons occupy the same orbital? Here's the Pauli Principle. No two identical fermions, now an electron is a fermion, can occupy the same physical state. So since we're just talking about electrons and no other fermions, then we're talking about identical fermions. Can occupy the same physical state. So here we have to define state. What is state? Does that mean the two can fit in the orbital or not? Well, here's the state. It's broken up into space and spin. The space is an orbital, and the spin, if you remember, is up or down. Here's a possible orbital: the bonding orbital or the anti-bonding orbital. Then there's the anti-symmetric spin, and this is called a singlet, if you can remember that from back in the spin fundamentals. Or, and this one's a little weird, spin up and spin down, or spin down and spin up. And then this one means it doesn't matter. This one doesn't mean, it means it doesn't matter which one is which, but it seems to indicate they both have to be different. So that one's got me a little buffaloed. So if we choose the lowest energy, then both electrons would be in this same orbital, and they would have opposite spins. And this would give us the result that the state, if we swap these two around, then we get a negative value. Now, in this case, the orbital is not different, but the spin is different as far as the sign or as the state goes. The S1 and the S2 are both this orbital. So those are symmetric. There's no change one to the other. But for the spin, that is different. It does switch sign. Because of this, notice this minus sign. If you flip these two over on the other side and swap it, it's going to change the sign of the value. Now, next video is going to talk about the Slater determinant, and this enforces this anti-symmetric policy. If that determinant, and I didn't write anything in the determinant because that's for the next video 5, but if the determinant, if you calculate the determinant and it equals 0, then something's wrong. That is not going to happen because it doesn't satisfy the Pauli principle. If it's not equal to 0, I'm not saying exactly what it is equal to, but if it's not equal to 0, then the conditions are met. So I hope that rounds up things a little bit and gives you the idea that when we add the two electrons in the hydrogen molecule orbitals, that they have opposite spins.